Hi students, I am Prashant B. Chandran, Assistant Professor, Automobile Engineering Department, SN80 Engineering College, Adur. Today, in this video, I am teaching you about a problem on the topic radiation, in specific equal and opposite parallel plates. That is our topic. Okay. Problem. Let us start. Two square plates each 1 meter by 1 meter are parallel to and directly opposite to each other at a distance 1 meter, comma, the hot plate is at T1 is equal to 800 Kelvin and has an emissivity epsilon 1 is equal to 0.8. The colder plate is at T2 is equal to 600 Kelvin and also has an emissivity epsilon 2 is equal to 0.8. The radiation heat exchange takes place between the plates as well as with a large ambient at T3 is equal to 300 Kelvin through the opening between the plates. Calculate the net heat transfer rate by radiation at each plate and to the ambient. This is the question. Okay. This question is equal and opposite parallel plates. Its dimensions are given as 1 meter into 1 meter and parallel to and directly opposite each other. Okay. At a distance 1 meter apart, the hot plate is temperature T1 and its emissivity is given as 0.8. Colder plate has temperature T2 600 Kelvin and its emissivity 0.8. They are separated by ambient temperature opening between the plates. The net heat transfer, we have to find out the net heat transfer by radiation. Okay. They are separated by radiation. It is a take place between the plates as well as with a large ambient at T3 is equal to 300 Kelvin. Okay. Just write the given data. This it is given as equal and opposite parallel plates. And T1 temperature of plates temperature of plate 1 T1 is equal to 800 Kelvin and temperature of plate 2 T2 is equal to 600 Kelvin and temperature of the ambient, that is T3 is equal to 300 Kelvin. Then A1 is equal to A2, that is the area of both the plates are same as 1 meter square and emissivity epsilon 1 is equal to epsilon 2 and emissivity epsilon 1 is equal to epsilon 2 is equal to 0.8. Then to find the net heat transfer rate by radiation to each plate and to the ambient. Net heat transfer rate by Q. This is the question. Solution. First of all, draw the plates, two equal and opposite parallel plates, that is plate 1 and plate 2. T1, that is temperature of hot plate T1 is equal to 800 Kelvin and T2 is equal to 600 Kelvin. This is an ambient temperature T3 is equal to 300 Kelvin. This ambient. MC for EB1, EB2, MC for EB3. sigma T3 raised to 4. Okay. Then resistances can be drawn. It is first of all EB1, that is emissivity power of both the plates are drawn. Then in between EB1 and EB2, okay, there is a surface resistance. Let the junction be J1 and J2, and then this is J3, which is equal to EB3, which is equal to sigma T3 raised to 4, and in between J1 and J2 and J1 and J3 and J2 and J3, there exists shape factor resistance, that is 1 by A1 of A1 F12, next 1 by A2 F23, then 1 by A1 F13. Okay, this is the concept, and in between EB1 there are surface resistance 1 by epsilon 1 by A1 epsilon and 1 by epsilon 2 divided by A2 epsilon 2. Then finding the resistances. It is first find the surface resistances, that is 1 minus epsilon 1 divided by A1 epsilon 1, 1 minus epsilon 1 divided by 1 minus epsilon divided by A1 epsilon 1. This is substituting the values. 1 minus 0.8 divided by 1 into 0.8, or 0.8 into 1, which is equal to 0.25. Also 1 minus epsilon 2 divided by A2 epsilon 2, minus epsilon 2 divided by A2 epsilon 2 is equal to 1 minus same value, 1 minus 0.8 divided by 0.8 into 1 is also equal to 0.25. Okay, then from HMT data book page number 91, for square side by distance is equal to 1 by 1, which is equal to 1. Then F12 is equal to 0.1. This value can be directly obtained from the HMT data book, page number 91. therefore F13 is equal to 1 minus F12 is equal to 1 minus 0.1 is equal to 0.9. Similarly, F23 is equal to F23 is equal to 1 minus F21. That is 1 minus F12, that is equal to F23 is equal to 0.9. Then 1 by A1 F12 which is equal to 1 by 1 into 0.1 is equal to 10. 1 by A1 F13, 1 by A1 F13 is equal to 1 by 1 divided by 1 into 0.1 is equal to 1.11, and 1 by A2 F23 is equal to 1 by 1 into 0.9, which is also equal to 1.11. Okay. Then at node J1, EB1 minus J1 divided by 0.25 plus J2 minus J1 divided by 10 plus EB3 minus J1 divided by 1.11 equal to 0. That is equation number 1. And at node J2, J1 minus J2 by 10 plus EB3 minus J2 by 1.11 plus EB2 minus J2 by 0.25 equal to 0. That is equation number 2. Okay. Where EB1 is equal to sigma T1 raised to 4 is equal to 5.67 10 raised to minus 8 into 800 raised to 4, get the value 23.22 kilowatt per meter square. Similarly, EB2 is equal to sigma T2 raised to 4 which is equal to 5.67 10 raised to minus 8 into 600 raised to 4 is equal to 7.35 kilowatt per meter square. EB3 is equal to sigma T3 raised to 4 is equal to 5.67 into 10 raised to minus 8 into 300 raised to 4 is equal to 0.459 kilowatt per meter square. Substitute the above values in equation 1 and 2. That is, substitute the above values EB1, EB2 and EB3 in equation number 1 and 2. You get J1 is equal to 18 kilowatt per meter square, 18 kilowatt per meter square, and J2 is equal to 5 kilowatt per meter square. Okay. Then heat loss by plate 1 is plate 1 is given by Q1 is equal to it is EB1 minus J1 divided by 1 minus epsilon 1 divided by A1 epsilon 1. 23.22 minus 18 divided by 1 minus 0.8 divided by 180.8. The answer is 20.88 kilowatt per meter square. Heat loss by plate 2 is given by Q2 is equal to EB2 minus J2 divided by 1 minus epsilon 2 divided by A2 epsilon 2, which is substituting the values. So that is 7.35 minus 5 divided by 0.25. We get 9.4 kilowatt per meter square. That is, then total heat received by ambient Q3 is equal to Q1 plus Q2. It is 20.88 plus 9.4, which is equal to 30.28 kilowatt per meter square. This is the answer.